Hello, everyone. My name is Jay, and I'd like to talk to you about how to build a Clojure dialect. Now, I've been working on a Clojure dialect for the past several years. It's called Jank. But before I introduce that, I want to say a couple things about my intended audience for this. I'm not talking primarily to, or at least I'm not expecting to talk primarily to, compiler experts. I'm not a compiler expert. Let's just make that clear. I am, though, a compiler dialect creator. Now, I'm hoping that you are all either a Clojure generalist who's perhaps somewhat interested in what goes into creating a Clojure dialect, or perhaps you're a Clojure developer who could be convinced into making your own Clojure dialect. We'll see. Now, my Clojure dialect is called Jank, which is a polarizing name, I know. However, this is a Clojure dialect built on LLVM and C++. If you don't know what those are, that's okay. Just imagine it as a native Clojure. Now, the goal is to be able to use Jank with anything from C, C++, Objective-C, Rust, and so on through LLVM. LLVM is magic, basically, makes that stuff possible. Now, I've been working on Jank for 7 years. I started in 2015. When I started on Jank, it was not a Clojure dialect. In fact, I think when I started on Jank, I didn't know what Clojure was. However, Jank was always a Lisp. It started out as a Lisp that was statically typed and had a lot of parametric polymorphism following what we have in C++. But throughout the years, I learned Clojure. I rewrote Jank, and then I rewrote Jank, and then I rewrote Jank, and then I rewrote Jank. And at some point, I knew Clojure well enough that I thought, well, shoot, why am I making my own language? It's inferior in basically every way, aside from the fact that it's targeting native. So why don't I just make a Clojure dialect instead and target native? And so thus, Jank in its latest incarnation is that. Now, why would one build a Clojure dialect? Like, here I am trying to tell you how to build a Clojure dialect, but you might have not ever thought, I'm going to build a Clojure dialect. Here's why you might build a Clojure dialect. Firstly, to get Clojure onto a new host, right? So we see Clojure on JVM, we see it on JavaScript, we see Clojure in bash-ish things with Babashka, and so on. But there are a lot of potential hosts where Clojure could be that are not on the slide. For example, what about Ruby? What about Python, right? There are some Clojure Python things, but that was dead last I saw it. Still, there's a lot that could be done with getting Clojure onto new hosts. Also, it's a great way to learn about Clojure and about compilers and about runtimes and so on. And also, if you're a masochist, it's a lot of fun. Sometimes it's also quite grueling, even for the masochists. Now, I want to talk about some terms of, no, not terms of engagement, that's a separate thing. Some terms of compilation. Before we get into this, I'm going to define some things. So, when a typical compiler works, we have some source code, we lexically analyze it, this is a term I'm throwing at you. We syntactically analyze it, there's another term, and we semantically analyze it. Now, a different way of thinking about these is lexical analysis is just tokenization, right? We take our source code, we turn it into a bunch of tokens. Syntactic analysis is where we take all of those tokens and we make some sense of it based on an understanding of what our syntax is for our language. And then semantic analysis is where we take that, what we got from our syntactic analysis, which is our parse tree, and we say, does this make any sense, right? But we also do things like, okay, this isn't just a list, but it's an if, right? But if I'm calling a function, is this thing even callable? Does this make sense? Is this deafened, well-formed, that's all semantic analysis. Let me make this a bit more concrete. Now, given some source, we have here the string def foo 42. Note the shape here. This is a string. Now, when we tokenize this, it doesn't matter how deeply nested the source is. We're going to get a flat sequence of tokens. Next, we syntactically analyze this. Now, in a lot of other languages, in fact, in most other languages, your parse tree is just some internal compiler representation. It's not actually runtime data. However, in Clojure, and I would imagine in other Lisps as well, we take that, we take those tokens and we read it right into Clojure data. So perhaps confusingly, def is highlighted here. But maybe the better way to visualize this would just be to put a quote in front of this list, right? This is a quoted list of data. And it's a parse tree in the sense that if 42 were a nested expression that has, you know, a map inside of it or something like that, then we're nesting here and building a tree. Now, semantically, to analyze this, we also have a tree. But each of the nodes has more information in it. So, for example, this is a def, and the name is some fully qualified var, which we're going to need to intern. And the value is some other expression which we've done some analysis of. So let's just review the shapes here one more time. We start with a string, we break that into a sequence, a flat sequence of tokens. We read that into Clojure data, and then we turn it into more abstract maps, which describe not what was written, but what was intended. I think that's about as academic as we're going to get in terms of terms, so moving on. Lexical analysis, we learned this one, tokenization. I'm supposed to be giving advice here on how to build a Clojure dialect, but I'm also intending to reflect on 7 years of building Jank. So let's do a little bit of that. With the initial version of Jank, I was like, oh, I just want to build a language. Lexing, parsing, that's boring, right? I want to get to the good stuff. I want to get to the fun stuff. So I skipped past all that by writing it in regex. This is not a lie. It's taken right from the 2015 source. I have an outer regex, which gives me some matches, includes comments as well, and then I loop through those matches, match them against the inner regex. It's functional code. But moving forward, later iteration, this also combines lexing and parsing, but you can use a declarative grammar. Now, this was using an EBNF-style grammar with instaparse, which is a great library. There are some real benefits to this. Ultimately, Jank was rewritten in C++, so I didn't end up sticking with this, but I think if you were to write a Clojure dialect of your own, you could consider this. Now, what we ended up with was perhaps what I would call a proper tokenizer, which actually just memory maps the file, goes through character by character, and returns a lazy sequence using a C++ iterator idiom, lazy sequence of the tokens, which is pretty neat because you can be evaluating the first form because you've tokenized it, syntactically analyzed it, semantically analyzed it, now you're evaluating it before you've even started tokenizing the next form. My advice here, skip the regex. Although it does lead to a fun slide several years later. Embrace declarative grammars if you can, and if you're willing to accept the trade-offs. The trade-offs being primarily one, performance, especially if your grammar is at all ambiguous, and two, error messages, because it's hard to know when, why things actually failed. If you write it yourself, you have a lot more control over both of those things, but hate to break it to you, you have to write it yourself. Now, for syntactic analysis, I don't have much to say here, except for you need your object model early. And this may be surprising if you haven't thought about the way that Clojure works or is built. Now, I talked about how that parse tree is just Clojure data. But that means that after you've done your tokenization, which is fine and could just be an internal compiler representation. You already need a way to represent lists and maps and strings and vectors and everything like that in your runtime, because that's your parse tree. So that means that actually just bootstrapping your language requires a lot of work up front before you can even get to semantic analysis. But having Clojure data as our parse tree, it comes in very handy, as we're going to see a little later. For semantic analysis, this is where I really struggled. And that's because coming from a background of C, C++, Rust these days as well, I imagine source code as something that I can just evaluate statically. Okay, here's my program, here's all my source, let me just evaluate it. Nope. My mind was blown again and again and again as I tried to find ways to do this with Clojure. It may be technically possible for someone who's more academic than I am and less of a hacker. But for me, it seemed practically impossible. And that's because you need to evaluate as you go. Now let me give you an example of this. Here's some Clojure code, perfectly valid Clojure code, maybe. Now, I have two top-level expressions. One, a function call. Inside of that, an anonymous function. Inside of that, a conditional. If some global is truthy, I'm going to define foo to sandwich. Okay? The next expression, foo. Is this a valid program? Maybe. Maybe it's a valid program on my machine, but not on your machine. And that's why you can't make assumptions about vars. But this didn't stick in my head. No, I kept thinking I could. So let me have another slide here. For those of you who are like me, you can redefine a var to have any other value of any other shape at any other time from any thread. You can also alter the var's root. You can also, for some vars, bind it, right? That's a mess. So what this means is when you're actually generating code, you say, oh yeah, this var has a function in it, and that function has one arity, and I know that right now, and so over here I'm generating a call to that function using the var, and so I can optimize that call so that it goes right to that arity, and I don't have to go through the vars. And then that var is replaced. And then the generated code that you had there is wrong, and it crashes. Well, it's C++, I'm writing this in, so it crashes, but maybe it throws an exception in a saner language. Now for evaluation, I have to get something off my chest here. I'm sorry if this sounds like ranting. Clojure is compiled. We all know this, right? Clojure is a compiled language. I checked Wikipedia. Clojure is a compiled language, okay? No, I checked clojure.org. Clojure is a compiled language. Clojure compiles to JVM bytecode. We know this. Clojure is a compiled language, except for when it's not. When is it not? Actually, a lot of the time. Everything on the left here. If you were to send this to the REPL from your editor, evaluate a whole buffer, evaluate a single form, doesn't matter. It's interpreted. It's not just-in-time compiled. Now, everything on the right, function expressions, lets, loops, which are a form of let, which was surprising to me, but makes sense, and try and throw. All of those require just-in-time compilation. Now, anything inside of those, like a function expression with an if inside or God forbid, a def inside, that will still be just-in-time compiled, but everything on the left is interpreted. Now, maybe that blew your mind, but here's a pop quiz. Take a look at this code. We have a few vars, top level. We're defining add, that's a function. I'm using def and fn here, but defn would effectively end up being the same thing. There's no trickery here, I promise. And we define 5 to some function call. 5s is some map. We have a top level when. We are doing some arithmetic, we're checking some equality, and we have a print line. How much of this is actually just-in-time compiled? Well, I gave you the answer in the last slide. Only the function. Every single thing else, if you were to send this through the REPL, is not just-in-time compiled. We don't generate bytecode for it on the fly. Instead, we just do the work. Now, why is that? Am I saying bad things here, that Clojure is interpreted? It's not just-in-time compiled? No, absolutely not. It's not just-in-time compiled because it doesn't need to be. In fact, since Clojure's compiler is so integrated into its runtime, that why would you generate code to just do the thing that you already have access to? You can just create a var because the compiler is right next to the runtime, right? It can just reach in and say, intern this var, set its root to this value, check this if by evaluating the value for it. So let me just show an example of this. This is taken right from the Clojure compiler, compiler.java. To be fair, I cleaned up the code a little bit. But this is the eval function for the def expression. Now the def expression, when we're talking about our source, lexical analysis, syntactic analysis, and semantic analysis, the def expression will be part of the semantic analysis category. This is basically a node in our abstract syntax tree, our AST. It has an eval function on it. This is where the interpretation comes in. And it says, if there's an init provided, which is a value, because the value that you provide in def is actually optional. You don't need to provide one. But if you do provide one, then we take the var and we bind the root. Now, var was previously defined by just interning the var. And similarly, if some meta was defined, then go ahead and set the meta and also set whether or not it's dynamic. Now, if we were to just-in-time compile this, what would we do? That, right? Except we would have to generate all the bytecode for it, and then we'd have to, I don't know, do whatever magic the JVM has for turning bytecode into something you can run, and then we would do this. But why not just do it directly? Now, I want to be clear, during ahead-of-time compilation, we'll actually do all three of these. We'll interpret some code, we'll just-in-time compile some code, but we're also going to be generating bytecode on the fly that we're going to save out as part of our class files. So that's kind of the most complicated case. We're actually doing all three of them. This was a big surprise, but it's actually just a performance optimization. Now, macros are the Lisp bread and butter, right? Can't have a Lisp without having macros. I guess except for the previous versions of Jank, which didn't have macros. I don't, maybe it wasn't a Lisp then. But this got me thinking. For this latest iteration of Jank, which is the true iteration of Jank, how am I going to do macros? And this becomes a question because when you look at a compiler that doesn't integrate so neatly into the runtime of the language, but is instead just ahead of time compiling to some source code, well, how do you call functions at compile time then, right? You need to implement some other interpreter for that. And I don't mean interpreter the way that I did in the previous slides. You need basically multiple implementations. You have your ahead of time compiled implementation, and then you have your runtime implementation of every function. It's a mess. It's not viable, except for the first iteration of Jank where I actually did all of that. And it worked. But you have to maintain two versions of all these things. And one is interpreted and the other is ahead of time compiled. So I was wondering when I went to create this latest version of Jank, well, how am I going to do macros? And whenever I wonder these things, I just wish, well, firstly, that I knew Rich Hickey. And secondly, that I could just call him up and ask him these questions. Because like if someone's going to know, then he's going to know, right? I don't know Rich. But I have the next best thing, which is a chat bot that's been trained on everything Rich has ever said and has been convinced that it's Rich. So instead I talk to this guy, who's also called Rich Hickey, but let's not confuse them. Now I ask him things like, well, what do you think, Rich, would be the hardest part of implementing my Clojure dialect on LLVM? And he says things like, well, Jay, the hardest part would be probably to get all the macros working correctly. I think that there's some complexity there if you're trying to do everything. What sort of complexity is there, Rich? Well, each of the macros has basically its own compiler, he said. Each of the macros has basically its own compiler. I really paused on this for a while. I thought, that's profound, Rich. But it's also just one of his hallucinations. It's entirely wrong. Because, like, macros are just functions. All right? Now, when you have a just-in-time compiler, macros are just functions. They have a little bit of metadata on them to say macro true. But if you remove that metadata, it's just a function. And then you can just call that inside of your Clojure code like you would normally. Call back to the parse tree being Clojure data. The way that this works is, well, if your parse tree is Clojure data, and you can just, when you're analyzing the code semantically, you get to semantic analysis. You can say, oh, I have a function call here, and there's a symbol here for the first form of the function call. Then you can look that up. You say, is that a var? Yes, it is a var. Okay, great. What's the meta on it? Does it have meta? Yes, it does have meta. Okay. Is macro true in there? Yes, it is. Okay, great. Call that darn thing and give it the parse tree. And what are you going to get back? Your new parse tree. So for Interop, you really need to figure this out. I'm telling this to all the people here I'm going to convince to write their own Clojure dialects. You need to figure this out. And the reason is, and you've heard this before, but I'm going to say it again and it's going to mean something more. Clojure is hosted. What do you mean by that, Jay? Clojure is hosted. What I mean by that is Clojure relies heavily on its hosted environment. Here's an example. If you want to do some socket programming in Clojure, does that exist in Clojure core? No. Will it ever exist in Clojure core? No. Here's my bet right now. So if it ever does, $100, hit me up. And Rich cannot do this as a joke. He's accepting. No, you won't. You'll have to reach into the host, right? You'll have to do some interop. That's the section that we're on. And you'll have to do the socket programming there. If I'm in Clojure JVM, I'll reach into Java and I'll do my socket programming there. If I'm on JavaScript, I'll reach into JavaScript, I'll do some WebSockets there. You need this. It's the same thing with the early Clojure core functions. In fact, all of the Clojure core functions that start off at the top of Clojure core, what are they? Well, they're just vars that do some interop, because all of this is just written inside of Java. Like, Clojure is just Java classes. Now for Jank, we have interop in the form right now of the lowest level primitive called native raw. And native raw allows you to actually just do inline C++, which sounds scary, and that's because it should, because it's C++. And then there's this odd set syntax in there. And for those of you who know C++, you're like, oh, is that like C++ 20 something? No, that's an interpolation syntax, which allows you to run Jank code inside of your inline C++ code inside of your Jank code. Now, for those of you hackers out there who are wondering, can you do a native raw inside of an interpolation, inside of some C++ code, inside of a native raw? Yes, you can. So have fun with that. But my point here is that conj, and this is actually the way that conj is implemented in Clojure core in the Jank compiler, just calls into ultimately a conj function in C++. And if you look at the way that it's implemented in like the JVM, Clojure JVM version, it's the same thing, except it calls runtime.conj. So all of these are just built on interop. And once you start with some Java classes, some Java functions, you define some Clojure functions around that. And then you define some more Clojure functions around that. And then you can start using those Clojure functions to define your other Clojure functions. By the time you get to the bottom of Clojure core, you have a lot of Clojure functions, right? And you can start using more Clojure functions. By the time you get to your application code, you have a whole bunch of Clojure functions. And you don't need to do interop as much. Speaking of clojure.core, I'm sorry that I have more regex here, but clojure.core is huge. Now, Clojure, it feels like a small language, I think, to a lot of us, but 551 defs and defins inside of clojure.core is not that small. I think it's a lot bigger than a lot of us realize. And you, as a future Clojure dialect developer, will need to implement all of these. And I do as well for Jank. So Clojure is big, but it's not just about implementing defs and defins inside of clojure.core either. Because there's the whole object model, the whole class hierarchy that exists as part of Clojure. Let me give you an example. ArraySeq. Now, ArraySeq is a sequence in Clojure that's quite prominently used. I think the most prominent case is probably for packing the arguments to a REST function or a variadic function, right? So where you have like ampersand args, right? Now, an ArraySeq inherits from aseq and indexseq and iReduce, and then iReduce inherits from iReduce init. Not so bad. So if you wanted to implement ArraySeq in your language because you want to implement packed vargs, packed args for variadic calls, then this is what you're looking at to implement. Except that aseq is not alone, and indexseq is also not alone. So you were just looking at one compiler feature. Oh, I just wanted to support multiple arities of functions. And now all of a sudden you're looking at this object model and you're like, do I need to do all of this? Like, is all of this even needed in Clojure? I don't know. I honestly don't know. In Jank, we have variadic functions, but we don't have nearly all of this. It's the same thing when you're implementing these functions inside of clojure.core, right? Because it may just look like one function, but then you'll see, oh, this function is actually backed by a class. And that class has specializations for different types. So navigating all this can be tough. Now, I have an abstract point here I want to make. That clojure.core is, or Clojure in general is a library. And this is an abstract point in that Clojure is just built on a bunch of Java classes. So I talked about the object model. I talked about all this existing inside of Java. And I would state that everything that you want to do inside of Clojure, you can do inside of Java. Because it's all implemented in terms of Java, right? So how do we handle our namespaces? Java classes. And a synchronized map. How do we handle our vars? Well, they're Java classes. And then they have some synchronized root for them. How do we intern vars? How do we create functions? How do we create keywords? All of these things are just backed by a Java interface. Now, Clojure is some sugar to allow us to do all of this Java work. But this, I think, is an important way of thinking about your dialect as you build it. Jank is to C++ as Clojure JVM is to Java. I have built a C++ library that has the object model. It has everything needed in order to work with Clojure, but it's just a library. And when you think about this as a library, then all of a sudden you have two audiences. One, people who are actually writing Clojure code. But two, people who are embedding your language into their existing applications. If you want to embed Jank into a C++ application, you need to use its API. You're not writing Clojure code to do that. You're writing C++ code to do that. But one would argue that in some ways you're still writing Clojure. What else? What comes after this? Well, I don't know. I haven't done all that yet. This is about as far as I've made it. But there are things like software transactional memory, implementing a REPL server, line against support, linting support, editor support, actually getting a community to use your dialect, and so on. Yeah, in summary here, Jank is Clojure on C++. It's a native Clojure dialect. That's my first point. Second point is we need more Clojure dialects, and all of you can help. Rich has a great quote from his effective C++ talk, and I'm talking about the real Rich Hickey here, not the other one. He says, if people who don't do databases can write programming languages, anybody can. And I would say if I can write a programming language, then anybody can. So here's some info on how you can connect with Jank, and I appreciate you all from coming.